So your experiment number 3 will be on the horn antenna measurements, and I believe all of you know what is a horn antenna. So in this experiment number 3, we'll try to plot the radiation pattern of horn antenna in E and H plane. E plane is the plane in which you have maximum electric field. H plane is the plane in which you have maximum magnetic field. And from the radiation pattern plot, we'll also try to find out what is the 3 dB beamwidth in both planes, E and H plane. 3 dB means power has been reduced by half. You find out the position for the maximum radiation, and you also find out the place at which, position at which, the power has been reduced by half. And you can find out the 3 dB beamwidth. Since we are plotting the radiation pattern in two planes, E and H plane, there will be 3 dB beamwidth for both the planes. So for narrow beamwidth antennas, you can find the directivity from the 3 dB beamwidth in the two principal planes. We'll use that formula later on. And we'll also determine the gain of the antenna by using two identical horn antennas. By using Friis transmission formula, you can find out gain of the antenna when you are using two identical horn antennas. Once you have the gain and directivity, you can find the efficiency. The ratio of gain divided by directivity is the efficiency of the antenna. So we'll try to find out all the antenna parameters. These are some of the equipment usually we use for this horn antenna measurements, and these are all required for something called microwave test bench, which people usually use. We use microwave test bench, which actually have all these equipments, and we usually use it for microwave engineering lab also in the undergraduate studies. If you have done similar kind of lab, then you must be knowing all these components. We are using the same components which are there in the microwave test bench, and we are adding just horn antenna because we are making the measurement. So here we are also having something called turntable. So turntable has this. Basically here all the angles are shown here. So when you rotate this turntable, you know at which angle you are measuring the fields. So you're measuring over, let's say, 0 to 360 degree. You won't be able to measure 360 degree, but let's say you are measuring from 0 to some specific angle. At which angle you are turning the table, you can actually read from this turntable. There's something like protector here, so you can measure the angle. So depending on what angle you are measuring, you can note down what is the power, what is the radiation pattern, all those things. This is BSWR meter, and I think most of you have already seen this in the previous lab also. Voltage standing wave ratio, it's actually measure the ratio of the maximum Bmax by Bmin. And this is the klystron power supply. Basically in microwave, we are measuring, let's say, the antenna radiation pattern for horn antennas, usually which works in the X band. Antenna itself is a passive device, so you need to give some supply to the power supply to the antenna, some source to the antenna. So that is actually taken care of by this setup here. You have klystron power supply along with the reflex klystron. No? These are actually microwave sources. So this gives you signal to the antenna. Antenna will start radiating. These are microwave sources. And we also have isolator. So we connect this isolator after the klystron power supply and reflex klystron, so that any of the wave which is reflected back from the device should not reach the source. Otherwise, source will be destroyed. Then after that, we also want to know what signal we are transmitting. So we want to know what is the frequency of the signal we are transmitting from the source to the antenna. That can be done using this frequency meter here. Frequency meter will give you what is the frequency of the signal which are transmitting in the waveguide. So this is basically a circular cavity. This looks like a circular waveguide. So circular waveguide, when you cut it, terminate it in two sides, this side and this side, the signal which was propagating inside the circular waveguide will get reflected and start resonating depending on this dimension here. So this dimension actually decides the resonant frequency of this cavity, which is basically a circular cavity. So when you rotate this, the height of this cavity will keep on changing. So there will be at one frequency, the height of the cavity will show you the exact frequency of the signal which is propagating inside this waveguide. So this is a rectangular waveguide. So here our fields or energy are propagating through the rectangular waveguide. You can measure that frequency of that fields which is propagating inside the rectangular waveguide by using this frequency meter. Then you have attenuator. Basically, signal which is coming out from the microwave source, you want to attenuate it as much as possible so that this detector, this detector mount actually works in a proper region. We want to use square law, so we want to make sure that this detector is working in the square law region so that we should not have very high signal power. So we want to attenuate it. So that's the purpose of this attenuator. It will attenuate the signal so that this detector is working in a proper region. So the purpose of this experiment is to plot the radiation pattern of the antenna, and you know the radiation pattern of an antenna is the 3D pattern plot of electric field strength. It can be power plot also. Usually we plot the electric field strength. You can also similarly plot it for power because we are actually making measurement in the far field of the antenna, so you can directly find out the power from the field strength because you know power pointing vector is half E squared by mu naught, eta naught. So half E squared by eta naught. So electric field and power actually is directly related. So once you plot electric field or power, it doesn't make much difference. But this is basically 3D pattern plot. You assume that antenna is enclosed by a giant sphere in the far field of the antenna, and you try to find out the field strength at every point of the sphere. So the variation would be with respect to r is fixed because you are considering a sphere, r is fixed, but theta and phi will be changing in the spherical coordinate system. So for every value of theta and phi, you find the electric field on the sphere of radius r, which is r is in the far field, and you plot it. That's actually the radiation pattern of the antenna. Then you'll come to know how is the antenna radiating fields. But usually very difficult to plot this 3D pattern on a 2D plane like this computer screen. Then what we do is we take two principal cuts. One is vertical cuts and horizontal cut. We also call this E plane and H plane, two principal cuts, and we actually plot the radiation pattern in the 2D pattern plots. Once you have this 2D pattern plots, you rotate one of them with the other, you will be able to get the 3D pattern plot. So it's merely because of the convenience. We usually consider E plane and H plane radiation pattern, but the actual radiation pattern will be 3D pattern. You can generate this 3D pattern from this 2D pattern. This is a typical radiation pattern of antenna. So you can see that main beam is this one. These are side lobes. Then at the point where you don't have any radiation is called the nulls. And the direction of maximum radiation is called theta max. This angle between the two nulls, first two nulls, is called beamwidth between first null. So these are some of the parameters you actually specified for the radiation pattern of the antenna. And the half power beamwidth is basically you have maximum radiation here. How much is the angle at which you get the half power of the maximum radiation is called the half power beamwidth. You will have two of them in both sides, this side as well as this side. This angle between the two half power in both sides is called half power beamwidth. We'll actually find this for 2D pattern planes for E and H plane in this experiment. So from the 3 dB beamwidth, you can also find out what is the directivity of antenna. This is usually true for a narrow beamwidth antenna. I've already defined what is half power beamwidth. And I have already told you that we are making measurement in the far field of the antenna. Far field of the antenna can be found out from 2d squared by lambda. D is the maximum dimension of the antenna. And lambda is the wavelength at which you are making the measurement. So if you are moving away from the antenna at a distance of 2d squared by lambda, you are in the far field of the antenna. We'll make measurement in the far field. This is the setup you have here. So the setup will have an oscillator. Oscillator here is the klystron power supply and klystron reflex klystron. After that, you'll also have attenuator. Just before that, you also have an isolator here. Isolator actually allows the signals to move only in this direction. It will not allow signal which has been reflected back to reach the source. So that source will not be spoiled. Then you also have attenuator so that I actually want the signal which will be detected by the detector mount here to be working in the proper region of this detector. We are using square law here, so this should work in the square law region, so that we need to attenuate the signal, otherwise it will not longer work in the square law region, this detector here. This is the horn antenna, and this is transmitting horn antenna, this is the receiving horn antenna. We are keeping it at a distance which is in the far field, usually around 100 centimeter it should be. Then you will make the measurement using the BSWR meter. So this is a block diagram. You have an oscillator, then after that you have an isolator, then attenuator, this horn antenna. Then we are making measurement in the far field of the antenna. Distance will be calculated. You can check whether this is correct or not by finding out 2d square lambda of the antenna. Then this is the receiving horn antenna. Then you'll have a detector. Then you'll make measurement using the BSWR meter. So this is a brief procedure for plotting the radiation pattern. Usually you need to set up the microwave test benches at the starting. You have to connect all the equipments in the order which has been given in the previous diagram. And here we are using same type identical antenna for transmitting and receiving horn antennas are used. And you actually align the axis of both antennas in the same axis line using the turntable. You can align it. So to satisfy the far field radiation pattern, you are making a distance of 110 centimeter between antennas. So I think all the millimeter in the diagram should be replaced to centimeter. You can usually calculate it. This will be shown by the tutors at the beginning of the experiment, how to calculate distance so that the antennas are working in the far field region of the antenna. So then you also set the variable attenuator to maximum deflection at the BSWR meter, and amplifier is also set for maximum sensitivity. Klystron, or you can either use klystron as a source or gun diode as a source. Gun diode is also another source for microwave frequency region. You align antennas at 0 degree. They should be aligned properly, and you actually make sure that they are working in the same plane, E plane, H plane, H plane. Then you will have to make the copolar measurements. If you are actually making, see, there are two measurements for the radiation pattern. One is copolar pattern and is cross-polar pattern. So when you make copolar radiation pattern measurements, you align the polarization of the transmitting antenna and receiving antenna in the same polarization. So if you keep the transmitting antenna for the E plane, and you have to keep the receiving antenna also for E plane. So let's say if you keep the transmitting antenna in the E plane and receiving antenna in the H plane, you can make the cross-polar measurement also. So you need to make both measurements, copolar and cross-polar. We want copolar to be very high and cross-polar to be very low for an ideal antenna. So attenuator is also adjusted for the maximum. Then, as I already told you, you have a turntable. So in the turntable, there is a protector. No? So you turn the antenna. So whatever you are making the turning on the antenna, you can actually read it using the protector which is fitted on the turntable. So you can make angle measurements at 5 degree, 10 degree, 15 degree, and so on. And so you turn the antenna. You can either turn the transmitting antenna or receiving antenna. Let's say we are turning the receiving antenna. We're fixing the transmitting antenna. We keep the antenna fixed at 0 degree. First align the antenna, both the antennas, keep it along the same axis at 0 degree. Then after that, let's say you turn the receiving antenna 5 degree, then measure in BSWR meter, then 10 degree, then measure the receive signal in the VSWR meter 15 degree and so on, you measure it in the VSWR for both directions. From there, you will also be able to read the 3 dB beamwidth when the power has been reduced by half. When you make this measurement 5 degree, 10 degree, and 15 degree, and so on, you will see a point at which power has been reduced by 3 dB in the VSWR meter. So usually this is a graph sheet used for plotting the radiation pattern for both E plane and H plane. So at, let's say, 10 degree, how much is the VSWR meter measurement, 20 degree, 30 degree, 40 degree, you plot it. Similarly, in this plane also you can plot it minus 10 degree, minus 20 degree, then you can have a radiation pattern, something like this. So from there, you can find out this is the maximum, how much is the half dB. You can half dB point, you can find out then this distance between these 2 points of half dB, 3 dB would be your 3 dB beamwidth, half power or 3 dB. Once you have the half power beamwidth for E plane and H plane, you will make measurement for both E plane and H plane. For that, you need to keep the horn antenna in E plane and H plane properly. This will be demonstrated by the tutors. So once you have the half power beamwidth or for both E and H plane, you can use this formula. You can derive this to find the directivity. Directivity is equal to 41,253 divided by half power beamwidth in E and H plane. This half power beamwidth would be in degrees, and this half power beamwidth should also be in degrees. If it is in radians, you can change the formula accordingly by converting the degrees to radians. So now we have the directivity, we have plotted the radiation pattern. What else we want to do? We want to also calculate the gain. So for the gain, if you want to calculate, you can use the Friis transmission formula, and by using two identical antenna, you can easily find out. So if you are using two identical antenna, gain of the transmitting antenna and gain of the receiving antenna should be equal. From there, you can find out what is the gain of the antenna. So this is the procedure. You keep the range dB switch of the VSWR meter at 30 dB position with gain full control. So you can either keep it 30 dB, 40 dB, or 50 dB. That will be shown by the tutor. So this is just one typical number. Range dB, you can put it depending on the power you are giving, it can keep on changing. Then you energize the Klystron amplifier for maximum output at the desired frequency like last time. Then obtain full deflection at VSWR meter with variable attenuator. Then you also obtain the reading of the VSWR meter at the receiving antenna and record it. So how do you find Friis transmission formula? Power received is equal to GTGR lambda by 4 pi d whole square. No? So from there, you know what is GTGR, PTPR. So for example, you want to find PR. PR is PT GTGR lambda by 4 pi d whole square. D is the distance between the transmitting antenna and receiving antenna. So how much power you are transmitting, you know it. So before making the measurement, we actually note down how much power we are transmitting from the transmitting antenna. Then after doing the measurement, you know how much power is received by the receiving antenna. So PT is known to us, PR is known to us. And GT-GR, since we are using identical horn antenna, GT and GR are equal to G. So in the formula, the only unknown is G. R, distance between the transmitting antenna, is known. Using the frequency meter, you can measure the frequency. Once you know the frequency, C by F. C is the speed of light divided by F. F is the frequency you are measuring using the frequency meter. Then you know what is lambda. So you know R, you know lambda, you know PR, PT. The only unknown is G. So you can find out what is G, gain of the antenna. So once you have the gain of the antenna, if you want to find the directivity, you just take the ratio of gain divided by the directivity. You get the efficiency of the antenna. So I think we have actually made the measurement for almost all the antenna parameters which are required for this experiment. Thank you.